Okay, start with some reminders. We have a field trip. I think it's the 12th. I do know, well, actually I've got a schedule right here. Yes, the 12th. It is a trip to the Nebraska Academy of Sciences. I will have a specific requirement for you to do. You can pretty much, within 2 hours, you can definitely complete everything that's required. It's a conference where college students from colleges around Nebraska are presenting posters and talks. So it's a scholarly meeting aimed for people like you. And so the goal is for you to go and to interact and see how scientists communicate. Because the way scientists communicate is different than the way other people communicate. I take, for instance, it wasn't until I started working here that I heard people talk about reading a paper at a conference. I was like, what does that mean? Apparently, in some disciplines, you go to a conference and people just read something. At a science conference, they don't read stuff. Every now and then you'll have somebody who doesn't speak English fluently and they read. But they talk about their research. And so they present about it, not read about it, because we figure in science that we can all read. And so just seeing how the discourse occurs, I think is a very valuable thing to our students. Mirabal.
Is that the same place that Oaken used to go?
Yes.
Okay.
Yes, it'll be Dr. Mogel's class and my class, I think, are the only two that are going.
What class?
Honestly, I don't know. But just like we talked about at the beginning of the semester, I'm sure he talked about at the beginning of the semester. Although probably half of you don't remember me talking about at the beginning of the semester, so that's why I'm reminding you.
I was very confused. I got an email saying, you're registered for NAS. I'm like, I'm what?
Yes, you are. Okay, so group projects. Hopefully you're getting down to writing up your poster. I talked with Dr. McNeil last week, and of course I forgot, the whole maternity leave. She is out on maternity leave now. Mm-hmm. So I need to be in charge of the posters instead of just saying, here, Dr. McNeil, here's our posters. And furthermore, things have changed, a new person's in charge. So I need to call them, and I will call them this afternoon to find when the last date is. I can turn them in for us to have it printed by our last lab period. Our last lab period is going to be when you are presenting your presentation and your poster. So for your presentation, you need to have a 15 to 30 minute presentation that involves every single person in your group, that shows what your project was, explains how it works, and shows it working. If you don't show it working, now show it working. Let's take a case like the cloud chamber. You found it's finicky enough, you can't guarantee it's going to work, right? Mm-hmm. But if you have the video or the stills, that will be evidence of it working, right? So you don't have to have it physically working right here. It's more cool if you can. But if you can't make it work, make sure you have that. And if you never got to work, well, that's going to count down on your grade a little bit, right? It's not like you're going to get an F if it didn't work, because you're graded on a number of things. And you'll be graded by other teachers, by your classmates, and by me. And it'll be a combined score, with the student score being 50% of the overall grade. So your scores do have a significant impact. But it's not just your scores. There's also mine. Mine and other teachers will be the other 50%. Yeah.
How much would it hurt us if our experiment, we can't get it to work?
If you look at the rubric, which is printed in the lab guide, you can see what percentage that is. And, it's only like graded 1 through 5, like a whole bunch of other things. So it's not going to doom you in any way. But it'll lower you, 3% or so at least. Yeah.
So as far as the presentation goes, I talked to previous classes, and they said they did a PowerPoint. Do you need to do a PowerPoint?
You do not have to do a PowerPoint. You need to do what you think will be effective.
Okay. So is your definition of effective just showing our poster and presenting off of our poster, or would something beyond that be more effective?
I tend to think having bigger graphics than the poster will be more effective. but people can prove me wrong on that, right? It is a value judgment, not an absolute.
So does that mean that the more you have, the better, or? I mean, we don't want to like go off of the poster and I wasn't proven wrong, that type of thing. So
when you say the more you have, the better, that of course brings up just bloat it, and it's not better if you just bloat it. You want to have the salient features. This is what we did. This is the theory of how it works. Here's it working. Here's why this is good to know. Right? You want to make sure you cover those bases. You don't need to just fill in every little detail that occurs. And one thing that I find super important is that you can show how it works. So take the one that I know the most about. They're making a radio. And so they need to say, okay, this here is the oscillator circuit that works because you have a resonance frequency that's 1 over square root of LC. And so we have an inductor and we have a capacitor, and they need to explain how it works. Not just so, we connected the circuit, we turned it on, and it worked. Is that clear? Right. Surprises are never good when it comes to a project. Lydia.
And then I wanted to go back to the field trip real quick. So we need to drive ourselves there, correct? Should we all go as like a big group of
we used to provide transportation, but it was very rarely used. So now we're just find your way there. If you don't have a way, I will have a car and can provide some transportation. Mike.
So about the field trip, where are we going?
It's Nebraska Wesleyan University is where the conference is held. So it's like 4 miles down 48th Street, and then you turn right. Okay, so let's get on and talk about physics. We ended with this problem. What did I calculate with this problem? The what?
The particles that decay.
I actually didn't calculate. Those are given in the equation. Now we're going to come back to this topic in a whole nother chapter. But what I calculated was how much energy was released, because we have Einstein's equation that says the rest energy is mc squared. And so we use these masses to calculate the rest energy of carbon-14 and the rest energy of the nitrogen-14 plus an electron. Because nitrogen-14 plus is missing electron. If I add the mass of an electron, that will give me the mass for a neutral nitrogen-14. We ignored the neutrino, but I pointed out that that is also there, and that's predicted because they weren't getting the right answers from experimental measurements versus the theory until they said there must be something else there. So the key to this was we were able to calculate the rest energy of carbon-14, the rest energy for nitrogen-14, and then we use Q for the symbol. The disintegration energy, the energy that's released, is equal to the difference in those two. So that's the energy, rest energy of the carbon-14 minus the rest energy of the nitrogen-14 in this case. And so we were able to calculate how much energy is released. Now, I'm not going to redo the calculation again. I'm going to have the number in 2 slides anyway. Along the way, we introduced a conversion factor to make life much quicker. That 1 atomic mass unit is 931.48 MeV per c squared. That makes it real simple to calculate because E is mc squared. So if I had 1 atomic mass unit, it'd be 931.48 MeV per c squared. It's rest energy then, multiplied by c squared. You just cancel those c squareds, and it's 931.48 MeV. Now, we have learned about some invariant things that are conserved. Here it says invariant because saying the speed of light is conserved sounds goofy at best. But the speed of light is invariant. It doesn't matter what reference frame you're in. The speed of light in vacuum is always going to be between friends 3 times 10 to the 8 meters per second. Right? It's not changing. We also have mass like somebody was telling me in chemistry class, they say conservation of mass. Well, mass is not conserved. So why does it say invariant? There's a difference. And I have to give you some historical perspective on how I get this wrong. When I was in college, I had to memorize the mass increase equation. We had length contraction, time dilation, and mass increase. Physics has changed their mind. We were taught at that point that we could either learn that mass is constant and E equals, well, I'll get to that in a minute, or we could learn that mass changes and E equals mc squared was the correct equation. Now we're very clear. We say the mass of an object does not change in reference frame. So if I have a mass of 100 kilograms measured, I wish it was 100 kilograms, it's not, measured in an inertial reference frame here, if I'm in a spacecraft, I'm going to measure that same mass. Somebody else, if they had a way of measuring my mass, would measure the same mass. So mass is invariant depending on their in any reference frame. But those aren't the only invariant things. And so we are going to deal with some more interesting stuff. And first, remember I told you that Newton's second law is only correct in this form when you get to relativity. The other form was an approximation that's not correct. So sum of the forces equal mass times acceleration, not correct. It's a good approximation if we're in an everyday situation. So if we use this in the work calculation, what's the definition of work?
Moving a force over a distance.
Okay. The general physics version was force dot delta x. The calculus-based version was force dot dx. And of course, the calculus-based ones are the correct ones. The algebra-based ones are approximations. So if I use that, then I can take this definition of Newton's second law and say that the net work is equal to the integral of dp dt dot dx. And those of you who are not in calculus class are going to look at this and say, what? I don't know that it's right for him to be spending his time on this. This is an algebra-based class. Well, here's the calculus for you. If you go through the calculus, notice that for gamma mv, basic moment, and gamma itself is a function of velocity. For those in calculus class, that means it's more complicated. When you do the work, you find that the net work, which according to the work-energy relation, the net work is always equal to change in kinetic energy, is gamma final mc squared minus gamma initial mc squared. And if that's the change in kinetic energy, then the original kinetic energy must have been kinetic energy initial, kinetic energy final. And so we define kinetic energy not as gamma mc squared. Right? You look at that, you're like, I said that was gamma mc squared was kinetic energy final, right? But no, that's not how we define it. Because this is a change. If it's a change, there could always be a constant offset. And so what we do is we define total energy is equal to gamma mc squared. Rest energy is equal to mc squared. And if I take total energy and subtract rest energy, I should have the only other kind of energy, kinetic energy. And so I should get kinetic energy, and we'll just use, well, I use Ke here. So kinetic energy is equal to the subtraction of these two. Oops, wrong thing. Factor out the mc squared. So that's how we get this definition of kinetic energy. So it's a constant offset from what I had above because you have, if you take the difference in kinetic energies, the mc squared part, the one mc squared part is going to subtract out. So the important thing to take home from this, kinetic energy according to relativity is gamma minus 1 mc squared. The rest energy was and the total energy is gamma mc squared. So now I think in the homework that's due tonight, I actually included using these equations. I had forgotten that I hadn't gotten through this slide. And so now we're there. Now you can do them. So kinetic energy, different equation. What does that mean about our old kinetic energy equation? Okay, redundant. That's probably the best answer. It was correct at slow speeds. At high speeds, it's incorrect. But at slow speeds, it had to be correct. So what we have is the complementarity. Not yet. This is just the things I just said. Once again, the things I just said. Complementarity. Yes.
So if you were to take that equation and apply it to the slower speeds, would you get a wrong answer then?
That's where we're going. That is where we're going. It's the right thing you're thinking. So complementarity says that, and we've already seen this once, that in the region of overlap, we have to have agreement. And so my kinetic energy equation that's new for relativity needs to agree at slow speeds with our kinetic energy is 1/2 mv squared. And so obviously, well, what is gamma minus 1? Gamma minus 1 is equal to 1 over the square root of 1 minus v squared over c squared minus 1. That does not look like, well, if we were to take this, this is what would have to be true for complementarity. So this would have to equal 1/2 v squared over c squared for complementarity. And it doesn't look like that. So now we're going to go through, and I'm not going to do the math, doing a Maclaurin series expansion for a binomial to the nth power. So this is, as you can tell, it's a calculus thing. But you can take an expansion for binomial and you can write it out like this. 1 minus x to the nth power is 1 minus 0 to the nth power, that's 1. Plus a negative 1 times n times 1 minus 0 to the n minus 1 power. Well, you can see down here what those break down to. And then if you take gamma, we had gamma raised to the 1/2 power. And so that means that I have my n is 1/2, and my x is v over c. V over c squared. Oh, and n is minus 1/2. I forgot because it's 1 over square root. That's why it's minus 1/2. So using this binomial expansion that comes from the Maclaurin series, then I have my first term is 1, right? Because the first term is always 1. And then my second term is minus n, so minus 1/2 times x, which is v over c squared. So I have minus negative 1/2 v over c squared. And then my next term, is going to have n minus 1, so that's going to be minus 1/2 minus 1 is minus 3/2 over 2, so make that minus 3 over 4, times minus 1/2 again, so plus 3/8 times x squared, so times this, and instead of squared, it's going to be to the 4th, and so on. But the key is, in what region were we looking to check? For complementarity, it's in the region of overlap. So what does that tell you about the speeds? What type of speeds did we use kinetic energy is 1/2 mv squared? And what? I still can't hear you, man.
High.
Not high. We use them at low. We use them at everyday speeds, things like 100 miles an hour, 1,000 miles an hour. We use them at speeds that are much less than the speed of light. And so if v is much less than the speed of light, v over c is a really small number. V over c squared is a really small number. V over c to the fourth power is really, really, really small. And so these terms with higher powers here, that v over c to the whatever power is negligibly small. So we just take the first non-zero term and say that's enough. And so that means we're going to use, for low speeds, gamma is approximately equal to 1 plus 1/2 vc squared, which is what we said it had to be here. We move this one over there, we would have that was what we needed. And so indeed, using this binomial expansion for low speeds, for speeds where v is much less than c, our kinetic energy equation agrees with what we've already learned.
So you should get like around the same answer.
Exactly the same answer.
Oh.
So that is a really important outcome, that we have more confidence in our relativistic kinetic energy because it agrees with our classical one at the appropriate speed limits. Now back to this nitrogen, the carbon-14 decay. It releases 156 kiloelectron volts when it decays. Let's calculate, if all of that energy is in the electron, how fast is the electron moving? So I have what's the equation for kinetic energy? MC squared. Notice it's easier because we don't have V anywhere except for in gamma. So we find gamma. Once we find gamma, then we find what V is. What is the mass of an electron? Well, yeah, let's solve this first for gamma without putting numbers in. So I'll have to divide everything by MC squared. So if I want to find gamma, and what is the mass of an electron? That's true. Actually, mine's not 19. Mine's 27, but 511 keV per c squared is the convenient one to use. And then multiply that by c squared. What happens with those c squareds? Cancel. And so I have 1 plus 156 over 511. That came out surprisingly simple, didn't it? And that's one of the good things. The work that we do in relativity is not that hard to do. It's just really confusing. So 1.3053. Kept a couple extra significant digits because I'm not done. Right? You want to keep all your digits until you get to the end. So now what do I need to do to find the speed?
Set the equal to that.
So I'm going to switch the positions of the square root and the gamma, or just invert both sides if you prefer to say it that way. And then I'm going to square both sides. And so I'm going to get 1 minus v squared over c squared is equal to 1 over gamma quantity squared. And then just rearrange that. And then square root. So if I take my 0.303, 1.303, excuse me, I didn't put that in the calculator, and I invert that, which I'm sure is possible on this calculator, I just don't know how. I think this is it. and I square it. I don't know this calculator very well. And then I take 1 minus that. And I messed up. Pooh. Well, I messed up my calculation. Did anybody else go through and not mess up the calculation? Try a different calculator that has buttons I won't screw up as easily on.
.642.
So V is 0.643. I got 3 instead of 2. You might have cut more digits than me.
27.
Yeah, okay.
So, yeah.
So that's how fast the electron comes off in that radioactive decay process. If all of the kinetic energy goes to the electron, which is a pretty good approximation. So that was using kinetic energy. That's why I did the problem, was for the practice of using that kinetic energy equation in a practical sense. Now, just a few more relations that I'm showing without proving. This E0, the rest energy, is an invariant. And from that invariant, we get a 4-vector, well, we get this invariant relation that says the total energy squared is equal to the rest energy squared plus momentum times c quantity squared. Like I said, I did not derive that. You don't have a derivation for it here. It would take us too long. We don't have enough time. That is another invariant, which is actually really useful. If we were to go to the problem that we just did, we could have said that the momentum is equal to momentum squared is equal to that relationship. That would have been another way of working it out, but that would have found the momentum rather than the speed. I'll talk a lot more about the momentum and speed. The momentum is a little more difficult for finding the speed because it has speed in 2 different places, in the gamma and in the V. But that gives us a nice way of calculating the momentum for any situation. This second equation here is going to be something useful for us when we get to Compton scattering. And that is simply taking the definition that E is equal to E0 plus kinetic energy. In this equation, K is the kinetic energy. And so this is kinetic energy times the rest energy. And so that just comes by plugging this into there. Not going to show, once again, the math, but that's a relationship that's going to be useful. And then this last one. You can find the speed from the momentum by taking P is gamma mv, right? That's the definition. And energy is equal to gamma mc squared. And so if I just divide, whoops, that's the right thing. If I just divide those 2 equations, then I'm going to have my gammas cancel, my m's cancel, and I have P vector, momentum vector over the total energy is equal to the velocity vector divided by c squared. And so that's where the last equation comes from. It's actually very simple, right? What's the difference in the 2? C multiplied across one of the c's. So you can find the speed in a relatively simple fashion from the momentum if you use the total energy. So these are equations that, as you're solving problems with energy in relativistic cases, you might find it's a lot easier to do it this way or that way. essentially you can solve those problems with any method you choose, but some are going to be easier and others are going to be harder. So that's why I show you these different equations. Now for another good question. What's the rest mass of a photon? A photon is the name for a particle of light. Yes. Which is our next topic, by the way.
D?
What'd you say?
D?
D is the rest mass of an electron.
Oh wait, light is massless, isn't it?
A is the answer. Who said that? A is the answer because light is not at rest. Right? Light is only moving. So the rest mass is kind of a trick question. What is the mass of light? Okay, so the answer that we give is 0. The rest mass of light is 0. And then when it's moving, it could have a calculable mass. And so we can calculate the equivalent mass for moving light. But if it were to be stationary, it would have a mass of 0. And how do I know that? Right? If it's kind of a trick question, you can't really define the rest mass. Here's how I know that. Total energy is gamma mc squared. How fast does light travel? Redundant question, right? Travels at the speed of light. What is gamma at the speed of light? I'm going to put it over 0 just so we're all good. Nobody says, it's not really infinity, it's undefined. Okay, we covered that bitch right here. What's the only way this can be a defined value?
If mass is 0.
Yeah, it can only be defined if the mass is 0. And in truth, if the mass is 0, what's its value?
0.
Indeterminate. Then you have to use things like L'Hopital's rule to go further. And what we will learn coming up real soon, it's equal to a constant multiplied by the frequency. So it's not 0, it's not undefined. It actually has a fixed value based on the frequency, which L'Hopital's rule with our equations here would not have gotten you there. So it does have to have a rest mass of 0, even though really you can't define the rest mass in a normal fashion. But in order for it not to have an infinite energy, it has to have a mass of 0. Anything that's going the speed of light is going to have a rest mass of 0. That makes some sense? Okay. A problem for you to do as a group. An electron has a kinetic energy of 1 mega electron volt. Find the electron's speed and its momentum. And I will write here just so you don't have to look back. And I suppose other equations you might use. I think that's enough to be able to do it. Actually, this equation might make life easier too.
So it's kind of eat. the equation for kinetic energy. So no, that's math.
Oh, okay, that makes sense. Yeah.
Oh, it's one.
I'll go through to get there. Okay, we only have 6 minutes left, and you can see that there's more than one way to do this. I saw multiple people doing it the same way that I started doing it before I realized there's an easier way to do this. So the brute force way, and it's not super hard, is to take this equation, since you know the kinetic energy, and find what gamma is, and once you have gamma, to find what V is. That's kind of the brute force way. The way that's a little bit easier is to take this equation. What's the total energy? Well, the total energy is kinetic energy plus rest energy. So we know the rest energy is 511 kilo electron volts, well, per c squared times c squared, if you want to be like, how did you know that? So that's the rest energy. The total energy is equal to the rest energy plus the kinetic energy. So that's 511 keV plus 1 MeV is 1,000 keVs. So having that total energy, then using the boxed equation, I have forgot to put the squares. I was like, well, that came out simpler than I remembered it. Yeah. So I've got to do the difference of those squares, and then I square root it, and I find that PC is equal to, and I'm trusting that I did my work right, 1422 keV. So that means P over C is 1422, P is equal to 1422 keV over C. So there's my momentum. It's not a standard unit of momentum, but it's the one we use in relativity because it's the convenient one. So now that I found my momentum, then I'm going to use the relationship that we just worked out. P over E is equal to gamma mv over gamma mc squared. Cancel the gammas and the m's. I didn't even have to calculate gamma here. I could have, but I didn't have to. And so that gives me V over C is equal to P C over E is equal to 1422 keV over 1511 keV, and that's equal to 0.941. So V is equal to 0.941 C. So I think probably shockingly to every one of you, the math wasn't hard. Isn't that a little shocking? There were different methods that would make the math harder, but they're still correct. And nobody's going to mark you off for using a harder method. At least not in my world, they're not. So if you were working at it from the standpoint of, well, K, if you started with this equation here, and you found gamma, that's great. And once you found gamma, you invert that to find V, that's great. And once you found V, then you have gamma times M times V is momentum. It all works out. It's a little bit longer mathematically, but it's still perfectly good. What do we see here? Well, number one, there's more than one way to skin a cat and still get the right answer. Creativity is going to make our lives easier, is the other thing. And how do you know which way to go? Honestly, when I started doing this here, I started using this equation because my mind immediately went to, well, that's the way you get from kinetic energy to speed. But then after I had done that calculation once and made a mistake, I looked back and said, wait a minute, there was an easier method. And if you're curious, my mistake was that I used the wrong. Actually, no, that wasn't wrong. I didn't make a mistake. Thought I did. I was incorrect. All right. We will start with this in lab tomorrow. Tomorrow's lab is going to be the photoelectric effect lab. At least I still believe it is. And that photoelectric effect lab is, well, we have to explain it before we do it. So that's why I'm going to lecture on it at the beginning of lab tomorrow. So have a great day, and I'll see you all tomorrow in lab.